I'm sorry, 4. So my question is, I mean, that series I just wrote, n equals 4 to infinity, is technically not the harmonic series, right? It's the tail of the harmonic series, starting at 4.
How can we do this then?
Oh, we can compare the tails. See this and this. Those are two series of the same kind. And you notice I've been somewhat, I mean, the thing is, so in the interest of not having to do this for every example, I will allow you to use the direct comparison test stated a little bit more loosely. So here's the kind of a loose statement of it. If this, for n much, much greater than 1, okay, then this is true. It really doesn't matter that these are negative. As long as eventually most of the terms in the series, beyond some point in the series, if all the terms are positive, then we can apply the test, is what it boils down to. Because if eventually it's always positive, then everything before that is just a number. Whatever that is, it doesn't spoil the convergence or divergence. It's either a number that you add to the sum, or it's a number that doesn't change the fact that the other rest of it diverged. But if you want me to be picky, I could say this test is only for series starting at 1 or something stupid. But we don't really mean that. I mean, so there's a certain nuance with these tests. You can apply them to the tail of the series, actually, to judge the convergence or divergence. And so, anyway, getting to the point here, this diverges, right? Have I done that? Son of a mother, this goat. Let's see here. What has become? Have I done this all for the wrong? Man, look at that. You guys. I've got the wrong inequality. This diverges. So I want to show this diverges, right? This is my known data, my P series, right? The harmonic series. I know this thing blows up. And great, so some series larger than my given series, term by term, diverges. That tells me nothing. There are several ways to fix this problem. The one is by adding a square to the n. The other is by changing the minuses to plus. Which would you prefer? Let's make a square on the n. That's more exciting. So n squared. 1 squared, 1 squared, 1 squared, 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 squared. Tail of P equals 2 series. There we go. Oh, phew, what a relief. The P equals 2 series does converge, right? So the fact that my 1 over n squared series, the fact that the 1 over n squared, and of course I didn't need to peel it off at 4 with this adjustment. We could have just kept the first 2 and just started at 3. We could have started the tail at 3 with my logic. But anyway, my point. This converges because P equals 2 converges, and the 1 over n squared minus pi series with that is less than that, right? Am I right about that? Am I?
Still thinking about what you said.
Am I right about that? Or was my mistake actually just that one inequality?
If you have a constant in the bottom, should it still be less than
No, we didn't need to do this. Sorry, guys. This is going on my course evaluation. Let's see here. Professor can't make up his mind. Keeps changing examples mid-course. Yeah, look, this is stupid. This is what's the nature of this denominator? Is it smaller than n? It is smaller, so this fraction is larger, right? Denominator, not numerator. That was the error. I actually did start the problem correctly, and then I managed to do that. Sorry about that. So we have a series of positive terms, which is larger than the harmonic series, at least the tail of it, so it diverges. So sorry about that, yes. So direct comparison, sometimes helpful, sometimes helpful. Let's see if I can do another one for you guys. Actually, I must go back to the geometric series before I forget. We'll get to the limit comparison tomorrow, most likely. Okay, guys? Geometric series. So you can derive that a plus ar plus ar squared plus dot 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 equals to a over 1 minus r for the whenever the we need the absolute value of the so-called radius has to be less than 1 in magnitude. Yeah. In other words, the sum n equals 0 to infinity of a r to the n is equal to a over 1 minus r for this condition. And this is the so-called geometric series result theorem, whatever you want to call it. By the way, if the radius, there's more you can say, and this guy, n equals 0 to infinity, a r to the n diverges whenever you have a radius which is greater than or equal to 1. I proved this yesterday basically by calculating the nth partial sum and then subtracting r times the nth partial sum for you. And I multiplied it by a today for our convenience. I had a being 1 yesterday, and I had r equal to x yesterday. Yeah.
Can you pull a constant out of you pull out constants?
Yeah, there are some rules for series, like the sum of the series of the sum is the sum of the series. Series of a difference is the difference of the series. If we have a series where we have, c times a sub I, then we can pull the c out. Yeah. Again, just like with limits, it's subject to the condition that the given series all exist. So, there's some fine print there. I should actually write those on the board maybe tomorrow. But yeah. So let me try my example from yesterday, foolishly again. Actually, I'll try example. I'm going to try a more famous example to start with. 0. Well, here's fine. I'll try my example. But for some reason, I needed to try a little bit different. I had 1.9999999. Okay. Anyway, the 9 repeats. All right. So this is 1 plus 0.9 plus 0.09 plus 0.009 plus dot, 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 dot. Let's see here. So I could look at this as being, let's see here. So by the way, if you write this out, this looks like what? Oh, I have it up here. So I think I need to just focus on this piece here as being the geometric piece. I think the 1 is messing with me. I don't know, but I'm sorry. Let me just stop being an idiot. So this is A, right? This is going to be AR. This is going to be AR squared. This is going to be AR cubed. If that's the case, is that actually possible? I don't think that's actually true. No. I can't do that because that's just not true. So what I should do is I should stop being weird and just look at this piece. So here I'm going to have A equals to 0.9, AR squared is my 0.09, and so forth. So what's my R given this? Zero 0.9 times what? Yeah, 1/10 to the I. Oh, I'm sorry. Why am I using I? I meant to use N there. I'm sorry, guys. What's wrong with me? My voice is giving out. So, excuse me. There you go. Now that's geometric. The radius is 1/10. The initial term is 0.9. So by the geometric series result, this is 0.9 divided by 1 minus 1/10, which is, of course, 0.9 over 0.9, which, by the way, is 1. So this stuff here converges to 1, right? So 1.9999 repeating is equal to? You knew this without calculus already, right? 2, yeah. It's not hard to show with geometric series that anytime we have a decimal number with a repeating fraction, like a repeating decimal part, if it repeats, you can understand it as a geometric series, and you can re-express the number as a rational number. With the geometric series, it's a simple matter to prove any number with a repeating decimal expression is actually a rational number. It's a quotient of integers. Yeah.
So like, with respect to the geometric series, like specifically, you could, since it is, since like it does, the powers like increase like that to infinity, can't you just like take like what you did like the first few, then add that one on it, and be like, okay, I know it's this, like I know what it's going to.
Yeah, right. I mean, my point was to, if I throw in the 1, it's not a geometric series. That's what confused me yesterday. Because I don't get from 1 to 0.9 in the same way I get from 1.9 to 1.99. To get from here to here, I add a 9th. To get from here to here, I add a, I don't know. There's something. To get from here to here, I add a 10th. You know, 1 to, no, I can't say it in words. Anyway, this is geometric. The whole thing is not. I'll try to explain that more cleanly. There's a test we can do on a given series to decide whether or not it's geometric. The deal is this. It's only geometric if you can take the ratio of any two terms, successive terms in the series. If that ratio is a constant, which we call R, it's geometric. If it's not, then it's not geometric. This is not geometric because if I look at 0.9 divided by 1 versus 0.09 divided by 0.9, this is 0.9, whereas this is 0.1. And in fact, the ratio between any two successive terms in this piece is 0.1, which is why this part of it is a geometric series, whereas if you throw in the first one, it's not. This is what messed with my head yesterday. Okay, more on geometric series later. Talk to you guys. Have a good rest of your day and so forth. By the way,